Then we'll continue Fourier series. And your textbook didn't talk, didn't have too much background on that Fourier transform. The last time we introduced Fourier transform by a limit of Fourier series, which actually should be, I mean, otherwise you just introduce an integral transform, you don't know what it is and why it is so. And especially the justification of how you get to why the Fourier transform and the inverse Fourier transform is correct. That depends on the concept that we skipped about delta function. But we can introduce the delta function by this limiting process also, because we have something similar to delta function we introduced when we divide the Fourier series. You can do the same thing for same limit, take the same limit for to see how you get the delta function out. So, let's repeat a little bit. The argument was you start with a Fourier series over a finite length, and now we go back to the case minus L to L, right? We fix that, and then Fourier transform basically a Fourier series with infinite domain. So basically, we need to set L goes to infinity, and then I take the limit of whatever the Fourier series formula. We go to the limit of large L. L goes to infinity. Then we get the Fourier transform formula. How you get to define the Fourier transform, the inverse Fourier transform formula. We start with the Fourier series in compact spaces, right? Remember that we have a function over minus L to L, then that's sum over n minus infinity to infinity. This is n. And now this is minus L to L, so the basis is only n by x over L. Right? Remember that. That's what we did by rescaling the base case from basically L equals to pi. Go back to the base. Go back to the simple the case with the period is 2 pi. So set L equal to pi, you get back to the formula. Right? And then the C sub n, we actually derive that because that is quite straightforward. If we assume that the function can be expanded, that this is called completeness. If we assume that, then C sub n is quite easily derived because you just substitute into this formula, integrate minus L to L and x. Convince yourself this is minus n x over n x. And the normalization is to L in this case. And that derivation is simple because you just substitute this into that, right? And then all these are just elementary integral. You know how to integrate exponential function, right? So when you convince yourself that when you substitute this to that, this is not n because n is a summation variable. Change it to m, right? And you convince yourself that e to the im pi x over l multiplied by e to the minus im pi x over l integrate over x over one period, and that would be 0 if n not equals to n, because all these are periodic functions, and non-zero when n equals to m, and it will give you 2 pi because the period is 2l because you integrate minus l to l and cancel with the 2l in the denominator, and you recover this formula. Only m equals n term survive in equals. Okay, that's how you divide, and it's elementary and rigorous, right? And then we also say that this is, you can write it as so-called orthonormal condition. It basically define a basis, just like basically this one divided by square root of this one, so 5 and the square root of 2 L. Then the orthonormal condition is just the scalar product. Yes. Delta N. Right, the conical delta. Right. That is just the symbol for 0 if n not equals m, and 1 when n equals m. Okay, so now we can see what happened when we go to L to infinity limit. We look at that and see what will come out, because when n equals to m, this is a discrete mode, but when we go to limit, remember that we change n pi of L as k, and then this becomes an integral, and this is no longer a discrete mode. And how do we write actually the orthonormal condition in a continuum? So let's just write it out explicitly. So substitute this into here, so you have 1/2L integrate. In this case, it's minus L to L. We have e to the I. This one's m. Both have a pi L by x in the L, and then yeah. Or let me just write it out explicitly. M minus I. So this is for m. When you do the scalar product, this become compact conjugate. So compact conjugate here, this one, and then the dx, right? And this convince yourself. It's fixed for to show this is conical delta. Okay. Now we do the same limit. Let L goes to infinity, and now there's a complication how you define something, transform this into something related to k. Eventually, we'll have a k here, right? And what can be done is that we fix a number, fix either one of them, n or m. So you fix n, fix for n in n, just choose the integer, and we sum over n, sum over all n, right? This means we sum over all m on the right-hand side also, and you see that this for any n, any integer, when you sum over all m, you will hit the case n equals to m exactly 1. So this summation is equal to this 1. Right? This is for all, for any n. All right. Then this becomes something that we can do the trick that we did last time, right? Because we argue that when L goes to infinity, this is an infinite domain, right? So L is large, so both of these m pi of L becomes undefined if we don't renormalize it, because L goes to infinity, everything goes to 0. That's not good. So we define it. So like m pi of L as k, and then now m pi of L becomes k pi. You can see that, right? So first you take the limit of L goes to infinity. Right. The first thing you do is renormalize that to I become k. This becomes k pi x dx. And the x now you integrate from minus infinity to infinity, right? And now what need to be done for the summation is that now we renormalize it. So m pi of L is k. This sum, because we integrate over the whole range, L is large, it means that we must, for any finite k, we must have m also goes to infinity to have a finite k, because k is n into L, k prime is n times L. For infinite L, so you involve for any finite k or k prime, you must have this n integer goes to infinity. It also means that when you doing the sum is infinitely dense, right? For any finite k range, infinitely dense, you have infinite number of integer of any delta k. So this sum is first changed to sum over dn, but dn you can change it to dk, but not renormalize that dk. Dm is dk multiplied by L divided by pi. Multiplied by L cancel with that, divided by pi give you 1 over 2L, 2 pi. Integrate from right. So that is the formula on the left hand side. And the right hand side should give you 1 because we already argued that this must be 1. Right. So now we rewrite this a little bit. Just we don't need to rewrite just with the bracket. Right. This is for any n. This means that for any k prime. For any k prime, this integral will give you 1. So this now becomes a function of k because we integrate over k with k prime as a parameter, which you choose as any real number. Any real number, you define a function using this bracket, define a function or something that you can put in the output in the integral. It always give you 1 for any k prime. Like, yeah. Yeah, from this taking limit, and we require that this object need to satisfy this equation, because this is how we take the limit, right? And we can take this limit, then we must require that in order that this is well defined, right? The limiting process is well defined. Okay, it turns out that is true, and then we use that quite often. So that's why I spend the time, because finally we will derive an equation that is very useful, very commonly used, and you should memorize that. This is one of the bases of when we do analysis, at least for physicists, we use this equation all the time. Okay, so that's why I spend more time to explain it, because it looks like coming from thin air, and then it looks like it's not well defined. You can look at this object a little bit more. This object defined by this square bracket. This is the integral in x, right? And it's an exponential function with this argument k minus k prime of x. And quite obviously, if k equals to k prime, exponential function is 1, and you integrate dx over the whole range, minus infinity to infinity, what do you get? If this is 1, you integrate over the whole 1. Why is it 1? I mean, this is 1, and when the exponential function becomes 1, you integrate dx over minus infinity to infinity, what do you get? You get infinity. So, right, so this, if you call it a function, this function has an infinite value at k equal to k prime for any k prime, right? And then for any k that is not equal to k prime, just maybe just a little bit off, no matter how small this is, what would that be? So that becomes an exponential function with a finite. This is like a wave number times x, right? It's wave number is just like the inverse of wavelength. So this wavelength is whatever large or small, but it's just oscillating in x space. Sinusoidal, there's a sine and cosine. You integrate over, keep integrating over large and large distance. And what do you get? Strictly speaking, what do you get? Say that again. You, how do you get that? I mean, strictly speaking, I mean, you look at this function, you integrate over k. Whatever k minus k prime define the wavelength. So this is 1, this is -1. All these are either real part, imaginary part, they're sinusoidal functions, just like this. You just integrate, keep integrating this thing. It it could be 0. It depends on where you end. Strictly speaking, it's not a very defined limit because I mean you can take that as a limit of like instead of minus infinity, the infinity change to just a large number, say minus and minus n, and then depends on where you stop, depend on what you choose, and minus n. You get different value. This integration, or I mean, once you define it, that integral is elementary. You can work that out. Just elementary integration by e to the I. A minus k prime x divided by I. A minus k prime evaluate right? That becomes a well-defined integral, and you can just substitute a limit, and then obviously this value will depend again because this is sinusoidal function. Whatever n which you get different value. Different n will give you different value. But what happened is that you take n equals to infinity. The end result of this is a function, oscillatory function with if I in the k space now is oscillating in the k space, whatever the n value is. But when n is large, this is oscillatory function with a extremely extremely small wavelength. So if you just stop at any n, function k, right? And as long as k not equals k prime, no matter how small that is, this is a function that is just oscillating. The wavelength is proportional 1 over n. You have to tend to see this function. I mean, there's also a profile. So there's a profile, the ADK. Actually, it's not this profile right here. 1 over k minus k prime. But this is k equal k prime. You get infinity. And k not equal k prime is oscillating like crazy. Right? So that is this object. That is this object. And normally you say this is not a well-defined integral, but we actually define it as a physicist in the sense that we put this in the integral. Everything like this, whatever, because this object we're putting it in the integration in dk. That becomes definable. If you just look at that is undefined because, like what I said, this function is oscillate like crazy. It's infinite at k equal k prime, and then once it's a little bit off, it's oscillate like crazy. Right? But when you put it in the integral, then all these oscillate like crazy. You multiply by anything that is well behaved, just smooth function, then all these oscillatory function, you integrate any finite range over this oscillating thing, you just give a zero contribution because you have positive and negative, and they just cancel each other. So all the oscillatory is canceling. So only phrase that will contribute to the final result is near k equal k prime because it's infinite, right? And so you pick up something that is at k equal k prime, and now there's at exactly k equal infinite, but just a little bit off. It's not. It's oscillatory. So there's a finite width that contributes to the finite value. So there's a limiting process to look at how large this contribution is. And you can look at this as that limiting process. All these well-defined limit that we start with something that is well behaved, that we know how to divide. This is what we elementary integral. We divide that, and now we take the limit and show that it must equals to 1 for any k prime. So the normalization must be that this one will, when you put in a k integral, whatever k prime is must give you 1. And that is what we define as delta function. That is defined as delta. Although we analyze it a little bit, this function is, I mean, if you define this object like that, in infinity at k equal k prime, auxiliary equation, there's a profile that the k1 over k minus k prime, but that actually doesn't matter because all these oscillatory will not contribute to the final integral, only pick up the contribution from k equal k prime, and the contribution normalized such that this is valid. So let's rewrite that. Let's rewrite that. This is important. So this is like orthonormal condition for Fourier transform. dk to the k minus p dx. I should say dx. This is actually this object dx. Equals to 2 pi k minus p. Or you can divide 2 pi over the other side. That's fine. This is exactly this one. So this is your orthonormal condition for Fourier transform. Right? So, and we divide that, kind of divide that from the orthonormal condition for Fourier series, and take the limit of L goes to infinity. And then we get this this relation. And in the meantime, we just get the property of this object that we define. Okay? This is what we call the delta function. Right? And so it has the property that we put in here will get you 1 because we integrate dk and multiply by this function or this object and give you 1 for any k prime, right? But if you generalize that, you instead of multiply by just 1 in this integral, multiply by any well-behaved function like g as gk as a function that is smooth, like his well-behaved is not another function that actually crazy. Then you put it in the integral. So dk is gk delta k minus k prime. Put this in here, then you get right. That's the property of delta function. Okay, so that is the orthonormal. So we generalize the orthonormal condition from Fourier series to Fourier transform, and we can also go back to another condition for Fourier series because we divide actually we first talk about a delta function using the Fourier series as what we call the completeness condition or the consequence of completeness. And if you remember when we define the Ortiz mode, and we can also talk about completeness like when you substitute this c sub n back to here, that becomes an integral. And in order that we cover that same function, we require that the sum over n. When you put in the here, you use like x prime instead of x. And now the condition is e to the, this become x prime, so I n I over L. Well, that must be Okay, now we can do the same trick as what if we take the limit. Say L goes to infinity, this become K, this integral become, this summation become dk, integral over K. But we need to normalize that. We multiply by L divided by pi. That's L tends to infinity. This limit is 1 over 2 pi dk from e to the r k minus x. Now this is still delta function. Okay, so that is another way we look at the delta function. And now you realize that this way, using the completeness condition, you get a delta function, and this equation is exactly of the same form as what we did for the orthonormal, because they are of the same form, except this is integration over x, this is integration over k, and the rest is the same. I mean, it's structurally the same. We just interchange x and k, and the delta function is delta function in k. This is delta function in x, right? They are the same. So for Fourier series, the orthonormal condition and the completeness condition is different. This is orthonormal conditions. This is completeness condition. But for Fourier transform, they are kind of the same, except you interchange k and x. This is orthonormal. This is completeness. Okay, but either one of them, you get this exactly the same mathematical equations. So this kind of integral expression for the delta function is very useful. We use that all the time, right? Yeah, from this step to this step, this to this. This one, L, when L goes to infinity. So this is the completeness that we define from we got from the Fourier series, right? And then now we take the same limit of L goes to infinity, and then we change this to K, like just like what we did before. M pi for L we define as K, right? And then let L goes to infinity, then the summation becomes integration over dn. This one becomes integration of dn. We change a variable, n pi over L is K, so we change the dk multiplied by L divided by pi. That is this one, and then there's 1 over 2 L here, and 1 over 2 pi. Okay. Which one? C sub n. This one. How I get this? Yeah, we put C sub. This is how we get this condition. When you put Cn over here, okay, let's write it explicitly. X equals to summation of n. And then we write when we put C sub n here, we change the integration variable to x prime, because more they have an x here. X prime, right? And then this is the C sub n here, and then we multiply e to the prime n x l. Right? And we require that this is satisfied for any function. Yeah, any function that, because we say any function, we can do a Fourier expansion like that, and that is called completeness, right? If any function can write like that, then we must require that this integration, we reverse the order, it's fine, and then put everything inside, the sum over 1 over t here, sum over n, and then the rest is just this two exponential function, I n pi over L. and multiply. We just rewrite the order. That's become the integration of x pi over any f, and we must recover the same f. And that is, so whatever inside this has the property of what we define as the delta function. And this is 1/2L. This is 1/2L. This change to 2 pi when we take the L goes to infinity limit. We go to L equals infinity. We change the n pi for L as k, wave number. Because L is going to infinity, we require n pi for L as finite, so we define that as a new variable k. Then this integration will be over dk instead of sum over n. It's integration over dk, and the normalization required that we multiply by L divided by pi. So change 1/2L to 1/2 pi. Is that okay? You follow that? Yeah, but I mean, and anyway, so that's finally we get whatever we get is the same. So one approach is orthonormal. We get the same mathematical function. And using completeness, we get exactly the same of the same equation that we define as delta function. Okay, but the final result is that this is important. So you should memorize this. This is one of the most commonly used tool. You can say it's a trick. Physicists like to use this kind of trick. Right? I mean, mathematicians like that also, but they will redefine something. They don't like something that is not well defined. You can build a theory, mathematical theory, to deal with exactly the same thing with more rigorous language. Okay. I think what the theory is something like distribution theory. So we don't call it delta function, it's a distribution. So you define a delta function only within the context of doing an integration. And as itself, this is not a well-behaved function. You only use it when you do an integration. Put it in an integram and multiply by something that is well-behaved. That you can work out the integration value. Okay. Okay. So that is the orthonormal condition and completeness condition for Fourier transform.